All right, so what we're going to be looking at now is we'll be taking some application problems and we're going to be rewriting these everyday situations in terms of parametric equations. And really what we're going to do is we're going to talk about curvilinear motion. So it's not just that you have a set of parametric equations, but we'll be able to look at those ordered pairs, and there's a t-value that gives us each ordered pair. And we saw that previously, like over here, we have a value of t, and it tells us a specific ordered pair for the x and y. So for curvilinear motion, what we're saying is that the t is representing a point in time, and the x and y that we get from that tells us the specific location at that time. So it's not just describing the movement like we have here as you go from start to finish, but we can say, okay, at any point t, any point in time, let t actually represent time, we know where a particular projectile is. And so it's really great for projectile motion like this. So if we say a cannonball exits the end of a cannon at a speed of 500 feet per second, if the cannon is angled at 25 degrees, so if its angle of inclination is 25 degrees relative to the horizontal, what is the maximum height that it achieves, and how far away will it hit the ground, assuming the ground is completely flat, right? And we're also going to make another assumption here that when we were launching this, we were launching it from the horizontal, okay? Now, before we jump into all of this, there's some things that we need to know. So when we have our theta, our launch angle, and we have our v sub 0 or v naught, this is going to be our initial speed. Here's how we set up our parametric equations. The way that you travel along the x is going to be v naught times the cosine of theta times t. And then our equation for y is going to be negative 1/2 g t squared plus the initial velocity times sine of theta times t plus h. So when we're talking about our normal everyday things, the g is going to be that acceleration. So this is the acceleration due to gravity. And that is going to be either 32 feet per second squared or 9.8 meters per second squared. In other words, your acceleration due to gravity is that you are accelerating at a rate of 32 feet per second every second. So your velocity is increasing by 32 feet per second every second of free fall. Now, there are some other physics things that we have to worry about in terms of, terminal velocity, wind resistance. But for a lot of these problems here, we're just going to neglect wind resistance and we're just going to go for it, okay? Because the differences are going to be kind of subtle and, well, it's a little bit more complicated than what we're talking about here. Again, this is really just to make sure we understand the concept of what's going on. So we have a speed of 500 feet per second at an angle of 25 degrees. So if you were to draw this picture out, here's the ground. You are starting off, we talked about vectors, right? So this goes back to vectors. So we have this angle of inclination here of 25 degrees and this initial velocity of, what do we say here? 500 feet per second. And so what we're going to do is we're going to break this down into the two components, into the horizontal and the vertical component, just like we did with the vectors, except now we have the component of time involved in this. So it's not just, what's the vector? It's let's draw the path of what's going on here. All right, so our parametric equations will be this. X of t is going to be our initial velocity, so 500 times the cosine of 25 degrees times t, and for the vertical, it's going to be negative 1/2 g. So we're talking about feet here. So let's use the 32 feet per second. So this makes this negative 16 t squared plus my initial velocity of 500 times sine of 25 degrees times t plus h. So we're making the assumption here that we're just starting at 0. And let's see what happens. Now, the question here is saying, what's the maximum height? So for maximum height, it doesn't really matter at all about what the x is doing. It's all about the y. So we want to know, where does y max out? Now, this could be a calculus question, but really, when we pay attention to what we're working with, we have t squared and we have t. So we have, because this is a negative t squared, we have an upside down parabola. And so we'd really just be trying to figure out, okay, what is the maximum value? What's the vertex? And we can find out what that value is, at what point in time we have that max value. So if you remember way back when, we talked about for the vertex formula would be negative b over 2a, comma, f of negative b over 2a. Well, all of this right here is your b value, and this is a. So we can really just kind of throw that into the calculator and see what we come up with, because really this is not going to be a pretty thing to do. Right? So that means we're going to have, let's see, we're doing degrees here, so let's make sure we're in the right mode. We need to switch over to degree. So I have negative, my b value is 500 sine of 25 degrees divided by 2a, so that's going to be divided by negative 32. All right, so we get that the max height is going to occur at about 6.603 seconds. Now that's the time that it occurs, right? We want to know what is that actual value, so we can just plug that into the y value here. So let's do this. So we got, I'm going to store this in for my variable, and we're going to evaluate this. So negative 16 t squared plus 500 sine of 25 degrees times t. And it tells me that we have a maximum height of about 698. We're talking about feet here, so max height is about 698 feet. The other part of this question is asking, when will the cannonball hit the ground, right? So the way that we can do this is we got to figure out when we hit the ground, what's the t value for where we hit the ground. Once I know that t value, I can plug it in here for the t and evaluate what that x value is going to be. So first off, I need to set this equation here. I need to set this equal to 0 to find my solutions. And this really isn't all that bad because I can factor out a t, and I'm left with negative 16t plus 500 sine of 25 degrees. All right, so when do we hit the ground? Well, the first solution is going to be when t equals 0. Obviously, that's where you start. The other part is whenever you take this and you set it equal to 0, which just means that we take 500 sine of 25 degrees and we divide by 16. So this other solution means that t is approximately 13.2 seconds. That's when we hit the ground. So that's the time where we hit the ground, but the question is how far away is that? So the how far away is not going to be using the y, but it's going to be using the x. So using this guy right here, plug it in there, and let's see what we get. So from here, x of 13.2. All right, so let's go to the calculator. We've got 500 cosine of 25 degrees times, and we're going to use our answer that we just got. So oh wow, that's a pretty big number. All right, so this is about 5,985 feet. That's how far away that cannonball is going to hit. Now, I want to put this into the graphing calculator so you can get not just an idea about what the graph looks like, but see how the graph is made, because it'll show you the motion. So we have 500 cosine of 25 times t. Then we have negative 16 t squared plus 500 sine of 25 degrees times t. So for the window, let's see. The maximum time that we have is says 13.2 seconds, so let's just make that 13.3 to try to get as much on there as we can. The t step, let's say 0.01, see if it'll hold that. X min, so the x is the horizontal position, so 0 is the min. The max we have here is about 5,985, so let's just make that a nice 6,000. And we'll make the x scale to be, let's say 1,000. The y min, lowest it gets is 0. The highest it gets we found to be 698 feet, so let's say 700. And a scale of 100. Let's see if this will work. Boom! Isn't that awesome? So that's what it would look like. As you trace it out, it starts right here at the origin. It goes up to this maximum height right here, and it crashes back down at the very end whenever t is about 13.2 seconds, and that's going to be almost 6,000 feet away. I think that's pretty cool. You see that as we graph that out, it is graphing out the arc, the path that cannonball takes. So it's not just, here's a picture. It's, we traced out the path of the ball. I think that's really cool. Let's do another one.